back to the garage. Tonight we're going to be discussing oxygen sensors. You might have also heard of an oxygen sensor referred to as a lambda sensor. And lambda basically is a fancy word that refers to an even fancier word. Stoichiometric. In a previous lesson we learned that stoichiometric means basically the ideal air-fuel ratio. And if the number 14.701 has popped in your head, then good, you've been paying attention. So that's 14.7 parts of air by mass to 1 part of fuel. So the oxygen sensor's job is a little different than all the other sensors under the hood. So we have a throttle position sensor, we have a MAP sensor, or a mass airflow sensor, or maybe we have both. We have a barometric pressure sensor, we have a crankshaft position sensor, a camshaft position sensor. See, oh no! Blue died. Okay. CKP, CMP, MAP, Baro, MAF, TPS, and the list goes on. These all happen before combustion. Basically, you turn the key on, all of these things are going to start sending signals, and your computer is going to use those signals and the programming to come up with an air-fuel ratio. The oxygen sensor's job is a little bit different. It's doing its work after combustion. It's in the exhaust system, and it's looking at the oxygen content to try to decide if the air-fuel ratio is right, and it's providing us something very valuable called feedback. So if you're at work and your boss tells you to do a job, but never really tells you how they feel about your performance, they never give you any feedback, you really have no idea if you did a good job or not, unless you're really self-confident. Well, our PCM is fairly self-confident, but it wants to be sure. So the O2 sensor is going to provide us with feedback, and that way we're going to be able to know for sure, is our air-fuel ratio as good as it possibly can be. Okay, so, one more time, all these pre-combustion sensors are going to provide us with some input, and we're going to start the car, and until our oxygen sensor starts doing its job, which it doesn't do right away because it has to get hot, we're going to be running in something known as open loop. So basically, open loop is when your PCM just keeps throwing an air-fuel ratio at the engine and hoping for the best. It's open. It really doesn't know what happened. It just knows that it did the best it could, and it's just going to keep doing that. So open loop is when you're running with no feedback. That's supposed to be a C. From the oxygen sensor. And by the way, we all know that O2 is another name for oxygen, so from here on out we're going to call this an O2 sensor. So basically the PCM is hoping that we're at the 14.701 air-fuel ratio, but it's going to just try its best. I should also clarify that we're not always going to run at 14.701. That's a great ideal air-fuel ratio for cruising conditions. It runs nice and clean, it burns clean. We're going to make the least amount of harmful emissions at that level, but under hard acceleration, wide open throttle, we're going to go richer than this, and there's going to be some times when we go leaner than this, particularly deceleration. At any rate, we try to stay out of open loop if at all possible. You're only in open loop, really, at cold startup. And on older vehicles, maybe for the first minute or so of running. On a more modern vehicle, first few seconds, maybe 10 seconds or so, you're in open loop. And our oxygen sensor technology is such that we can get into what's known as closed loop much, much quicker. So cold startup, wide open throttle on some cars. When you stomp at wide open throttle, it will revert to open loop. Basically, that's more common on older cars where they really don't trust the feedback coming from the O2 sensor to be accurate enough at wide open throttle, and they want to make sure that they don't go lean and burn the engine up at wide open throttle. We don't want to burn pistons and detonate. So we try to stay out of open loop if at all possible. The other time you might find yourself in open loop is if there's a trouble code, if there's some sort of fault. So some sort of massive engine management fault, like the loss of a key sensor, like maybe a mass airflow sensor or something like that. So if we lose a necessary sensor input, we're basically in a limp home strategy. We're basically in a do whatever we can to make the engine run enough to get the driver of the vehicle out of harm's way and to safety. So we try to stay out of open loop. What we want to be in is closed loop. So closed loop is when we listen to all these guys and the O2 sensor. So our engine's here. Our exhaust system is here. Our oxygen sensor is right here. I'm going to draw a nicer picture later. Our throttle is here. And our injectors are up here. So here's my PCM. Actually, let's change colors here for our O2 sensor. So the O2 sensor provides feedback. Basically an input. And therefore our PCM can give us a better, more reliable output. So that's our loop. We send an output, we send a control to these fuel injectors, squirt some fuel in, we get some feedback from our O2 sensor, and we fine-tune the results. We fine-tune our actions until we get a good operating condition. So that's what we mean by closed loop. So O2 sensors have been around a long time. They first came out somewhere in the 1970s, and they came out basically hand in hand with catalytic converters. So your catalytic converter is really sensitive to the air-fuel ratio that the engine is burning and how much oxygen and how much unburnt fuel is passing through it. So we want to make sure that we're giving that catalytic converter the best air-fuel ratio we possibly can. So we came up with this concept of oxygen sensing, and I believe it was Bosch that came up with it first. This was back in the 70s. The technology obviously back then was not quite what we have now. And what they came up with is what was known as a narrowband O2 sensor. And what I mean by that is the narrowband O2 sensor. By the way, I suppose I should probably show you an O2 sensor by now. The narrowband O2 sensor threaded down into the exhaust system pretty close to the engine. It would screw into the manifold, and it looked at the oxygen in the exhaust passing by it. And what it was able to do is it was able to tell the computer at the time, is the engine running rich or is the engine running lean? But that's all it could do. Rich or lean. It's the best it could do. What it couldn't do is tell the computer how rich or how lean. Basically all it could do was tell rich or lean. And it did this in kind of a really simple way. Here's my exhaust pipe. Threaded down into the pipe, and it had some holes in it so that gases could pass through it. And if we were at stoichiometric, if we were at that 14.701 or lambda, this thing would actually produce a voltage of about 0.45 volts. So at the stoichiometric ratio, this thing produced 0.45 volts. If the voltage went above that, that meant we were running rich. If the voltage went below that, it meant we were running lean. So less than 0.45 volts lean, more than 0.45 rich. And it would only go up to about a volt, and unfortunately within that 0 to 1 volt range, there wasn't really any correlation. There was nothing that would really say like, oh, at 0.8 volts, you're exactly 12.2 to 1 air-fuel ratio. It didn't work that way. Basically, it was only accurate right there at stoichiometry. So 0 to 1 volt output, 0.45 was perfect. More than 0.45 too rich, the computer would take away fuel. Less than 0.45 lean, the computer would add fuel. So this worked okay for many, many years, and it kept the cat happy. So the catalytic converter, that was right here in the exhaust system, worked very, very well, with occasionally getting a little too much oxygen, and then occasionally getting no oxygen, or a depleted state of oxygen, and then occasionally getting flooded with more oxygen, and then occasionally getting depleted. So what you ended up with is a system that kind of fluctuated. This thing would indicate rich or lean, less being lean, more being rich. And so the computer would constantly keep shifting, rich and lean, and rich and lean, and rich and lean, based on the signal that came in. But the signal would fluctuate. So this would be rich, this would be lean, this would be rich, this would be lean, and the computer would just do the opposite. Every time the signal said rich, the PCM would go lean to the injectors. Every time the signal said lean, it would go rich. So it fluctuated. Fluctuating signal coming from the O2, fluctuating signal going to the injectors. I should note that the signal that goes to injectors, as we're going to find out in tomorrow's lesson, does not look like a sine wave like this. I'm just trying to represent rich and lean. Okay? So, making sure I'm covering all my points here. We got our narrowband sensor that can only indicate rich or lean. And this worked for a number of years, and there were some refinements to it. They sort of changed how they did it over the years. I suppose before we talk about refinements, we'll talk about the type of sensors. So the first type was what's called a zirconia sensor. These things make 0 to 1 volt, and they basically work by a chemical reaction inside with the oxygen inside them and the oxygen outside them. So if this was the sensor, it'd be a hex, there'd be some threads, there'd be a little shield with holes. And there'd be a wire coming out of it. Just one wire. How'd I do? You might notice this one's got 4 wires. We'll talk about that in a minute. So, the amount of oxygen here in the exhaust system is much, much less than the amount of oxygen out here in the atmosphere. And it worked based on that differential, the difference between how much oxygen is out here versus how much oxygen, I can't speak tonight, is in the actual exhaust pipe, in the exhaust. If you're burning rich, if you're spraying too much fuel, you're going to pretty much consume all the oxygen in the combustion chamber. There's going to be almost no oxygen here in the exhaust. With that big, big, big difference, that's where it makes the large voltage, the huge 1 volt signal. With a lean mixture, you'd have extra O2 left over. And with extra O2 in the exhaust, there's less of a difference. You're going to make less of a voltage, hence the lower voltage. And this thing would basically be perfectly balanced at about that 0.45 volt range. So again, this worked pretty well for a number of years. A couple of things they wanted to refine. When the first sensors existed, they only had one wire, and that was your voltage, 0 to 1 volt. Let's go up here. The one wire is the signal to the computer. The threads of the sensor would provide the ground where it's screwed into the exhaust system. At some point, some manufacturers decided that the exhaust system wasn't a very good ground. If you've ever seen an exhaust here in New England, then you know that they're not too good looking. They're pretty rusty. So they were probably right. So we came up with 2-wire sensors, which had a signal and a ground. So a separate ground wire. Then we get a little more advanced. We came up with a 3-wire sensor. And this is where stuff got interesting. Reminder, we're talking about zirconia sensors here. A zirconia sensor has to get hot in order to operate, and somewhere in the 600 to 700 degree range. So you might think, okay, it's threaded into the exhaust system, it's definitely going to get hot. The closer to the engine, the quicker it would heat up, but that's not necessarily the best place to read the oxygen content. If you can back away from the engine a little bit, you get more of a mixing effect from all the cylinders, so it's maybe a little bit of a better signal, but it starts getting cooler. And the other problem is it takes a while to get to that temperature at cold startup. So when we came up with this 3-wire sensor, basically we had a signal wire and a heater. They built in a heating element inside here. So that one signal wire we had in the beginning is still there, and now they've got 2 wires for a heater. One of those is going to be 12 volts, and one of those is going to be ground. And the computer would control either the 12 volt side or the ground side to turn that heater on as necessary. Some of them would turn the heater on only at startup, and then once the sensor got up to operating temperature, the heater would shut off. Sometimes the heater would be pulsed by the computer after you were at higher operating temperatures, just to kind of help maintain the temperature of this zirconia element inside there. And basically, suffice it to say, this gets us into closed loop much faster because it heats the sensor up faster. The last refinement there was the 4-wire sensor. A signal and a ground. And a heater. Positive and negative. So, signal, ground, heater plus, heater minus. There's your 4 wires. That's what you're going to find today. If you're still using a narrowband sensor, which some cars still do, it's going to have 4 wires. Matter of fact, I don't think I've ever seen too many 3-wire sensors, or 2 wires for that matter. Mostly 1s and 4s. These 2 and 3-wire sensors. That was kind of a quick period in time. So, 2 of the wires here are for the heater. 2 of them are for the sensor. I don't know which ones are which right now. I'm going to make mention of one quick thing on this sensor here. This one's out of my van. It's out because it failed. They can fail over time. Oxygen sensors can fail from contamination. If your engine burns a lot of oil, that can contaminate the O2 sensor. Sometimes they just fail and there's really nothing wrong. My van doesn't burn any oil, but this sensor did fail. I knew it failed because the car had a check engine light. It had a trouble code for this sensor. It can fail a couple of ways, by the way. The sensing portion can fail, so something with the signal of the ground wire. Basically, that 0 to 1 volt signal is not getting to the computer. or the heater can fail. And maybe this was a heater failure, I don't remember, I changed this thing quite a while ago. But the heater can fail, so you will set a trouble code if the heater fails. Okay. Somewhere around the late 1980s, somebody, I'm not really sure who, came up with the concept of what we call a Titania O2 sensor. These all had 3 or 4 wires because they were always heated. Always had a heater. They were always found on, well, I won't say always, they were mostly found on Nissan vehicles. So late 80s, early 90s. And by the mid 90s, this technology was kind of outdated as well, so these things started to kind of fall by the wayside. You're probably not going to find too many late 80s, early 90s Nissans still running around on the roads, at least not up here in New England. So the Titania sensor kind of is gone. The difference was, instead of producing a voltage, this thing varied resistance. And of course, I have to do my nightly check to see if my camera's still running and if I'm getting everything in the shot. Yes, I am. Looks like I've got about 4 minutes left and I'm going to run out of video time here. So, these were both narrowband sensors. Zirconia and Titania sensors were what we call narrowband sensors. I think what I'm going to do, in the interest of making sure that I don't get cut off in the middle of a sentence, I think I'm going to stop this video and start a second video on wideband sensors. So stay tuned for wideband O2 sensors.